Hello, in this video we're going to be using L'Hopital's rule in order to improve our ability to determine limits. So what L'Hopital's rule says that if you are trying to find the limit and we get a 0 over 0, we're going to find later that also infinity over infinity works. We can take the derivative of the top and bottom and then be able to determine what that limit is. These two limits work out to be the same thing. So an example that we've seen before is the limit as x approaches 0. We knew this thing to be 1. We just kind of said that, but why? Well, if we do direct substitution, we get the sine of 0 over 0, and the sine of 0 is 0. So we get that 0 over 0, which is what L'Hopital's rule is looking for us to do. So to determine what this actual limit is, we can take the derivative of the top. So our limit is going to be equal to the derivative of the top, which is cosine x, and then derivative of our bottom, which is just 1. Note that I'm not using the quotient rule. I'm individually determining the derivative of the top and the bottom, just like we would with a limit, just looking at what's the limit on the top and the limit of the bottom. Then when we plug that in, the cosine of 0 is 1, so that is going to be just a 1. That is why we get that limit. L'Hopital's rule is really cool. It works with 0 over 0, and it also works with different types of infinity over infinity. However, there are certain cases where we get these indeterminate forms where it doesn't work. When we come across these indeterminate forms, our goal is to convert our inside of the limit into one of these things that we do get nice, and then find that limit instead. We'll see some examples of those in a little bit. In this example, you can see over here, it's the old way that we did our limits. We rationalized that numerator in order to figure out what our limit was. We could alternatively use L'Hopital's rule. First, we check that we have one of the good indeterminate forms. If I do direct substitution here, I get the square root of 16 minus 4 over 6 minus 6, which does get us 0 over 0, the square root of 16 being 4. Minus 4 is 0. So we are allowed to apply L'Hopital's rule. So this limit is going to be equal to the limit as x approaches 6 of the derivative of our bottom, which is just going to be 1. Ooh, that'll be nice. And then the derivative of that top part. That's going to need a chain rule, so I'll get a 1/2 x plus 10 to the negative 1/2. And then when we do our direct substitution on this, we'll get a much nicer value. We'll get a square root of 16 in the denominator, because that 1/2 exponent, and that'll be 1/8. Same limit, but found in different ways. This example with our previous work on limits, we weren't able to figure out. We had no tools in order to evaluate this limit. So we just said, I don't know. So we're going to check if we can use L'Hopital's. We always need to check first if we can apply L'Hopital's rule. So this with direct substitution would be the ln of 1 cubed over 1 squared minus 1, which equals, let's see, 1 squared minus 1, that's 0, and the ln of 1 is also 0, so we do have that 0 over 0 situation. If we don't have 0 over 0, or infinity over infinity in some version of positive and negative, we're not allowed to apply L'Hopital's rule. So we always have to show that we can first. So now that we can, let's do it. So this limit is going to be equal to the limit as x approaches 1. We do the derivative of that top part. So that is 1 over x cubed multiplied by doing a chain rule, the derivative of our inside, which is 3x squared. Note that I'm not doing quotient rule again because this is just doing the derivative of the top over just the derivative of the bottom. And then in the bottom, we get 2x. That's it. That's it. Okay. Now I could do work to simplify that down, but I'm about to do the limit, so let's just plug in that stuff. So that is going to be 1 over 1 cubed times 3 times 1 squared over 2 times 1. And this will be a lot easier to simplify. Well, 1 over 1 cubed, that's 1, times that 3 that is going to be 3. In the denominator, we have 2. So that is our limit, 3/2. Let's see if we can use L'Hopital's rule on this problem. So first, I check with direct substitution. I get the ln of 1 over the sine of pi. So the ln of 1, that's 0, over the sine of pi is also going to be 0. So yeah, that is 0 over 0. So we're all set to apply L'Hopital's rule since that direct substitution failed. So I get the limit as, oh, underlined. What am I doing there? X approaches 1. The derivative of the top is going to be 1 over x over the derivative of the bottom. Derivative of sine is, I don't know why I'm changing colors here, cosine pi x. We then have to apply a chain rule, so the derivative of the inside is going to be pi. Okay. Again, I could simplify that, but why bother? I'm about to put a 1 in there, so let's do that. So we get 1 over 1 over the cosine of pi times x times 1. So that's the cosine of pi, and then all that is multiplied by a pi. So in the numerator, we've got a 1. The cosine of pi is 1. Oh, I was worried it was 0 for a second. So cosine of pi is 1. So that is a 1 times pi. So our limit is 1. Don't make me big. 1 over pi. Let's see how L'Hopital's rule applies to this problem. We have a limit as we're approaching infinity. Via direct substitution, we basically get infinity cubed over e to the infinity squared. So that numerator is going to be very large, and that denominator is also going to be very large. So based on L'Hopital's rule, we are all set. We've got an infinity over infinity. If one of these had been negative, we still would have been okay. So let's take a look at what's happening with our derivative. So this is equal to the limit as x is approaching infinity of, let's see, 3x squared over e to the x squared multiplied by doing a chain rule to x. And then we would try to direct substitute this thing, and we would end up with, well, it's still infinity over infinity. Like that numerator is going to be infinity, and that denominator is going to be infinity too. So I really haven't solved anything. It's still just infinity over infinity. We could do a little bit of work of, like, we could cancel these x's here. So now it is the limit as x is approaching infinity of 3x over e to the e to the x squared. But still, we're still no any better. This is still, the limit is still infinity over infinity. Well, the cool thing about L'Hopital's rule is you can L'Hopital's rule a L'Hopital's rule. So we'll just do it all again. Why not? Since we still have infinity over infinity for our limit, you can see how that numerator is kind of calming down. It's not as complicated as it was before. So let's just do L'Hopital's rule again. So now we have so this is using L'Hopital, filling in some stuff there. The derivative of the top is now just going to be 3 over, and that's going to be a chain rule again. So it's going to be basically what we got before. So e to the x squared multiplied by a to x. Now when we do direct substitution, we get 3 over something very, very large. So 3 over basically infinity. So that thing is going to head towards 0 because we have such a large number in the denominator. In this example, we're trying to figure out what indeterminate forms are being obtained by this. So when we do our direct substitution, this thing is providing a infinity, and when we plug in infinity, and then we get a 1 over infinity. So we get infinity to the 0. You can see how this is not that 0 over 0 or infinity over infinity, it's not giving us one of our good indeterminate forms for L'Hopital's rule. So we're not allowed to just take the derivative of the top, and we don't even have a bottom. So we can't do L'Hopital's rule right now. So we want to manipulate this thing a little bit. Here's my plan. What I want to do is this limit equals something, we hope. So let's set it equal to y. Why am I doing that? No, whatever. I want some value, so I've got like at both sides, and we know it's going to equal something. So if we can find something else out, maybe we can get somewhere. I've got that exponent, and my plan for that exponent is I am going to do an ln of both sides. I can do something to both sides, kind of like solving an equation, because I've made an equation that this y, that's the value I'm looking to determine. I want to figure out what that y value is. I'm going to kind of try to solve for it. So now we have the ln of y, and I'm going to do something. This is the final sneaky thing I got to do. Since I'm doing the ln of a limit, natural log is a continuous function. So as we're putting values into natural log, nothing weird is going to happen. So the limit of what's inside of there is going to be the same as we did if we did the ln of all that stuff. There, I just typed up what I just said. We can just pull that thing in there. If we were trying to do that with like a divide or something, that is not a continuous function, so we would not be able to do this trick. So now I'm trying to figure out what's going on with this thing. All right. Well, the trick with ln, and it's why I picked it, is we can take whatever is inside of that natural log and pull it in front. So we can take that 1 over x and put it in front of the ln of x, which then makes a fraction. That 1 over x going in front becomes basically a divide by x. So now let's check it for L'Hopital's rule. This thing is going to, the numerator will head towards, if we put infinity into natural log, it will head towards infinity. The denominator will also head towards infinity. We have an infinity over infinity, so we can apply L'Hopital's rule to find this limit. We get the derivative of the top is going to be 1 over x, and then the derivative of the bottom is going to be just a 1. Now, if we evaluate this limit, the numerator heads towards 0. 1 over infinity is basically 0, and the denominator is just a 1. So this is all equal to 0. Now, that's not the limit I'm looking for. That is telling me that the ln of y equals 0. But I wanted to figure out what is y. Y was my original limit, so I need to figure out what this y value is. Well, that just takes a little solving. We can raise both sides to the e. So then we just get a y equals e to the 0, and e to the 0 is 1. So this limit up here is actually 1. This is our limit. In the final part of this problem, here is the limit that we just found. So that's how you want to write your answer when you're done. I plugged it into the graphing calculator and I got this graph. So it's doing some weird stuff, but we can see as we're getting larger and larger values, it is heading towards this line right here, which is 5, 4, 3, 2, 1. Yeah. So it's approaching from the top. But hey, it's still heading towards 1. So hey. In this example, we're trying to find the indeterminate forms. This one is infinity minus infinity. I want to talk about y. This x value is approaching 2 from the right. So if we think about right here, as we approach from the right, we're going to get a positive value from those two because we're going to have some value that's a little bit bigger than 2. And the difference between those two values is going to become smaller and smaller and smaller. So it's going to become a very, very small value. If we divide by a very, very small value, that's really like multiplying by some really big value. It's becoming bigger and bigger and bigger. And if we multiply by a really big value with this 2, we're going to head towards infinity. Same logic can be applied to this x squared. Since this limit is heading towards infinity minus infinity, we can't apply L'Hopital's rule right away. Even though we've got those fractions, it's not the thing that we want. So what I want to do is I want to try to combine those two fractions to see if I got a single fraction and then apply L'Hopital's rule to that. I can get a common denominator with these two things if I multiply that second fraction by an x plus 2. Then this multiplied by an x plus 2 will match with this x squared minus 4, difference of squares. So this will be minus x and then an x plus 2. So, we'll close that up. So then I'm going to do a little bit of simplification of that numerator. So we get the limit of negative x squared minus 2x plus 8 over x squared minus 4. With direct substitution, if we're approaching from 2 from the right to 2 squared minus 4, that's going to be basically 0. And then in the numerator, we'll get negative 4 minus 4 plus 8, which is 0 over 0. So we are set now to use L'Hopital's rule. Taking the derivative of that bottom, I'm going to do that first. So that's just 2x. In the numerator, we get negative 2x minus 2. Yeah. Okay. Then direct substitute. So we get, let's see, that is going to be negative 4 minus 2 over 2 times 2, which is negative 6 fourths, which is negative 3 halves. So that is our limit. Writing my answer nicely here of negative 3 halves equals that limit. We can also check this on the graph. So I graph the line y equals negative 3 halves, and here is our graph of this idiot. So you can see as we come in from the right, as we approach 2, we're heading towards this value of negative 3 halves. Huzzah! So ends our video on L'Hopital's rule. A reminder that we are able to just take the derivative of the top and the derivative of the bottom in order to figure out what our limit ends up being. If we have the format of 0 over 0 or infinity over infinity, positives or negatives as you please. However, if it is one of these idiots down here, we need to do some manipulation, some pre-work before they're able to join the L'Hopital ambulance to get derivative dead. Okay? All right. Thanks. Goodbye.